Okay, so today we're going to talk about saturated and unsaturated hydrocarbons. Um, so many people turn to greasy foods when they want a snack or a quick way to re-energize themselves on a busy day. The reason that these foods are known to be a good source of energy is that they all contain a significant amount of fat. Gram for gram, fat contains more food energy than does any other type of nutrient. These foods also share something else in common. It is likely that they all contain saturated fats and industrial produced fatty or trans fatty acids. So um, there's a few foods there, and it talks about the amount of industrially produced trans fatty acids. So how does the arrangement of hydrogen atoms around the double bond of a trans fatty acid influence its properties? Why is Health Canada working with food services and food processing industries to limit the content of trans fatty acids in food sold in Canada? And how are trans fatty acids made? Why did many manufacturers deliberately start adding trans fatty acids to processed foods in the 1980s? Fats and oils are both organic molecules that are rich in carbon and hydrogen atoms. To answer the preceding questions, once again, you need to look at carbon compounds and their bonds. So we have saturated hydrocarbons. So we already know that each carbon atom needs to have four bonds to be stable. So for example, each carbon atom in an ethane molecule is stability because it is attached to 3 hydrogen atoms and another carbon atom. This makes a total of 4 bonds for each carbon atom. As a result of having a maximum number of bonds, carbon atoms are stable and no other atoms can be added to the molecule. Since each carbon in ethane has 4 bonds to 4 individual atoms, it is called a saturated hydrocarbon. It is possible for a two or is it possible for a two-carbon molecule like ethane to exist with fewer hydrogen atoms? So look at what happens to a molecule when this occurs. If those two neighboring carbon atoms each lose one hydrogen atom, they can form a double bond. And if they lose an additional hydrogen atom, they can form a triple bond. So this is ethane and it's stable with its full outer energy level. And if we go to make a double bond here, so we have 2 hydrogen atoms leaving the carbon chain, then both carbons have an unbonded electron, so they are not stable until these unbonded electrons form a bond. So the closest thing to bond with is the electron from the other hydrocarbon. So both carbons form bond with each other to form a double bond. All carbon atoms are again stable, and the complete structural diagram shows the twisting that occurs to accommodate the double bonds, making a triple bond. So 2 hydrogen atoms leave the carbon chain on either side of the double bond, and the carbons are not stable until they form a bond. So they bond again, yet again, with each other to form a triple bond. And each molecule is stable in this molecule. The carbon each have 4 bonds, 3 from the other carbon and 1 from the hydrogen. So note hydrocarbons with double and triple bonds are less stable than those with single bonds. So molecules with double and triple bonds are called unsaturated hydrocarbons. They have been given this name because they are missing the maximum number of bonds to hydrogen atoms. Because there are fewer hydrogen atoms in unsaturated hydrocarbons, they have a general chemical formula different from the saturated hydrocarbons like alkanes. So a saturated hydrocarbon is a hydrocarbon containing only single covalent bonds between carbon atoms, and unsaturated hydrocarbons is a hydrocarbon containing a double or triple covalent bond between carbon atoms. So the difference between animal fats and plant oils. So have you ever wondered why many foods containing fats and oils are so popular? In addition to being a rich source of food energy, these ingredients provide taste, consistency, and stability. They also help you feel full. Although many fats and oils help to maintain good health, others do not. So to sort this out, you have to look at the shape of the molecules. So the molecules of fats and oils found in foods consist of 3 connected chains of fatty acids. The properties of fat or oil are determined by the particular fatty acid in these chains. So a fatty acid in an organic molecule consisting of a long chain of carbons with a COOH group at one end and a methyl group at the other end. So here we've got stearic acid and oxalic acid. Stearic acid is, it's consistently, it's straight, almost saturated hydrocarbon, and then it's got the acidic group at the end, where oxalic acid has a double bond in there. So what accounts for the different shapes of the two molecules? Looking closely, you should notice that the carbon chain in the stearic acid is a saturated hydrocarbon, whereas the oxalic acid from the plant oil has a double bond and is unsaturated hydrocarbon. That is, the carbon chain with the stearic acid contains only only single bonds between carbon atoms, and the carbon chain in the oxalic acid contains at least one double bond. Notice that the unsaturated oxalic acid has a bend in the chain at the location of the double bond. The two missing carbon atoms on each side below the double bond create a gap that allows the molecules to bend. This bend means that the group of oxalic acid molecules look like crooked twigs. They do not pack together closely in nice straight chains like the stearic acid, and since the oxalic acid molecules are further apart, this forces the attraction between the adjacent molecules are weaker. Therefore, it takes less energy to separate these molecules so that they can move freely over one another. This helps explain why oxalic acid is a component of an oil which is liquid at room temperature. The closer packing, the greater force of attraction between the molecules, and helps explain why stearic acid is a component of a fat, which is a solid at room temperature. So oxalic acid is an omega-9 fatty acid, and the end of the molecule with the COOH group is called the alpha end. This part that terminates with the methyl group is called the omega end. Since the double bond occurs within the ninth carbon counting from the omega end, this is an omega-9 fatty acid. Your body can produce small amounts of omega-9 fatty acids, but you can also get it from your diet through olive oil, almonds, and other nuts. It is this bent shape of this molecule due to its arrangement of the double bond that accounts for many healthy properties of this nutrient. In general, unsaturated fats and oils are healthier choices than saturated fats. On food labels, unsaturated fats and oils are often called monounsaturated fats and polyunsaturated fats. The first part of each word has been added to describe the number of double bonds presented in the molecule of each substance. Mono refers to one double bond, and poly refers to more than one double bond. So monosaturated fat is a molecule that includes fatty acids having only one double bond, and a polysaturated fat is a fat molecule that includes fatty acids having more than one double bond. And an essential fatty acid is a fatty acid that the body cannot synthesize itself and must obtain from food. So essential fatty acids, although it has become quite popular for people to reduce the amount of fat in their diets, not all fats are health hazards. In fact, some fats are essential for good health. That is why fat is often included in the ingredient in an energy bar. It is important to ensure that you eat foods with fats and oils that contain essential fatty acids. You need these nutrients nutrients for the formation of a healthy cell membrane, by the proper development of brain and nervous system, and for the production of hormone-like substances that regulate body function, for example, blood pressure. These essential fatty acids are the omega-3 and omega-6 fatty acids. Most people have no trouble getting enough omega-6 fatty acids, but it can be a challenge to get an adequate supply of omega-3 fatty acids. Sources of these include flaxseed, salmon, and sardines. So naming hydrocarbons with double or triple bonds. You already know that an alkane is a hydrocarbon that contains only single bonds. A compound that has at least one double bond between two neighboring atoms is the longest continuous chain of carbon atoms called an alkene. The compound that has at least one triple bond along the longest continuous chain of carbon is called an alkyne. The rules for naming alkenes and alkynes are similar for the naming of alkanes, except for the following differences. So if a compound is an alkene, the suffix -ine is used. If the compound is an alkyne, the suffix -ine is used. The double or triple bond must appear in the longest continuous chain of carbon atoms. The number of the chain is so that the carbons with the double or triple bonds receive the lowest possible number, and the location of the double or triple bond is communicated by a number placed before you name the longest continuous chain. So an alkene. So a hydrocarbon that has at least one carbon-carbon double bond, and then an alkyne is a hydrocarbon that has at least one carbon-carbon triple bond. So name each carbon given. Well, this is got two carbons, so that means it's got the eth in the front. It's got all single bonds, so it's ethane. So this carbon uses the suffix -ane because it is an alkane, and it has only single bonds between the carbon's atoms, therefore it is ethane. This has got a double bond, so it's going to be ethene. And this has got a triple bond, meaning it's going to be ethyne. Okay. So identify which diagram has correctly identified the parent chain of the alkene molecule. So A or B. It says here that diagram A is incorrect. Even though diagram A identifies the longest chain, this chain does not include the double bond. Diagram B is correct because the parent chain includes the double bond. So identify which diagram correctly numbers the carbons of the parent chain. So 1 through 4 going from left to right, or 1 through 4 going from right to left. So diagram A shows the double bond occurring after carbon 3. This is not the lowest number. Diagram B shows a double bond occurring after carbon number 1. Because 1 is less than 3, diagram B is correct. So correctly name the following hydrocarbon. This particular one here, we're going to follow the steps on the next slide. So the double bond for this molecule is between carbons 1 and 2. Use the smaller number to communicate its position. Therefore, the name of the hydrocarbon is 1 here for where the double bond occurs. 3 is for where the methyl group occurs. So we've got 3-methyl because the methyl branch is on carbon number 3, and then 1-butene because ene, meaning there's a double bond, and after carbon number 1, and then it's got 4 carbons in it. Saturated and unsaturated compounds in food. So we've just finished exploring how many different hydrocarbons that exist. And you know there are alkanes, alkenes, and alkynes. As stated earlier, butter is produced from fat-containing saturated carbon chains and therefore has properties more like an alkene. Margarine, on the other hand, is produced from oils containing primarily of unsaturated carbon chains and therefore has properties more like alkenes. So which is the healthier food choice, butter or margarine? So part of the answer to this question lies in the difference in the physical and chemical properties of saturated and unsaturated compounds. Remember that the physical properties of a substance include a substance's state at room temperature, solubility, color, melting, and boiling points. The chemical properties of a substance explain how stable and reactive a substance is. There is a relationship between the properties of different groups of hydrocarbons and their chemical structure. In the next investigation, we'll have the opportunity to identify trends that explain why this may exist. So melting and boiling points. Generally speaking, the boiling points and melting points of hydrocarbons increase as the number of carbons in a molecule increase. This is for 2 reasons. So the attraction between the molecules increase as the number of atoms within those molecules increase. If the attraction among molecules is strong, more energy or heat is required to break those attractions to cause a change in state, and then more energy is required to move something with a greater mass. So if a molecule is bigger, even more energy or heat is required to make it move. Therefore, a large number of carbons in a molecule results in a higher melting or boiling point for the carbons because of the stronger attraction between the molecules and the greater mass. Smaller hydrocarbons such as methane, ethane, have weaker attractions between the molecules and exist as gases at room temperatures. Pentane and octane have more carbons, and these compounds tend to be liquids, where waxes tend to have 20 carbons or more in their molecules and are solid at room temperature. So the reactivity of hydrocarbons. The reactivity of hydrocarbons depends on other molecules around them. As a general rule, unsaturated hydrocarbons are more reactive than unsaturated hydrocarbons. As a general rule, unsaturated hydrocarbons are more reactive than saturated hydrocarbons due to the bond strain between the double and triple bond carbons. If you make a molecular model of a double bond or a triple bond, you will notice some stress or tension in the bond. Recall that each spring in your model kit represents a pair of electrons shared between 2 atoms in a double or triple bond. Carbon atoms joined by double and triple bonds have a greater number of electrons between the carbons than singly bonded electrons. The larger number of electrons result in greater force of repulsion between them. As a result, the hydrocarbons with the double or triple bonds are more reactive than those with single bonds. The reactivity of unsaturated hydrocarbons is useful, especially when you look at industrial processes that use chemical reactions to produce different products. Many plastics and artificial rubbers are produced from the chemical reactions that involve unsaturated hydrocarbons. As you'll see later, the breaking of a double or triple bond, in short, unsaturated hydrocarbons, can be used to form long chains of single bonds. So the reactivity of hydrocarbons. So here's ethene and ethine. So if you recall that all electrons have a negative charge, there is a tendency to repel each other. The close proximity of the electrons within the double and triple bonds will increase the repulsion forces between the electrons. This repulsion force increases the stress within the bond and therefore increases the reactivity of the molecule. So origins of industrial produced trans fatty acids. Since butter tends to be expensive and vegetable oil is less expensive, it seems to be a good idea to make a spreadable fat from vegetable oil. However, it is not easy to manufacture a new fat which was soft enough to spread smoothly on a piece of bread. Early attempts to produce a product was too hard. Eventually, food scientists developed a process that could produce an artificial fat from vegetable oil. Margarine is made by bubbling hydrogen gas through hot vegetable oil under pressure in a metal vat. This results in the carbon double bond is broken and is replaced with two single bonds to the hydrogen atoms. Since two more hydrogen atoms can be added to the molecule for every double bond that is broken, this process is called hydrogenation. Hydrogenation is the reaction that converts carbon-carbon double and triple bonds in unsaturated compounds to carbon-carbon single bonds in saturated compounds. So if the hydrogenation is complete, all the double bonds have been broken. The result is a fat that is so hard that cannot be spread like butter. To solve this problem, the oil is only partially hydrogenated. This process is a soft, spreadable fat called margarine. The high temperatures needed for this partial hydrogenation process seems to have an unintended effect on some of the unsaturated molecules that remain in the vegetable oils. See if you can spot the difference in the figure. Okay, so we're going to look at it here. So, before being subjected to high temperature, it's got a very good bend in it. But then after being subjected to high temperatures and pressure, it's kind of more straight. So although it may be obvious that the molecule after being subjected to high temperatures and pressure is no longer bent, it is not obvious why it occurred. Look at the position of the hydrogen atoms on either side of the double bond. In the original oxalic acid molecule, the hydrogen atoms are on the same side of the double bond, providing a gap to the molecule to bend. In this elastidic acid molecule, the hydrogen atoms are on either side of the double bond, making the molecule more symmetrical so the hydrocarbon remains straight. The position of the two hydrocarbon atoms is what makes the elastidic acid molecule an industrially produced trans fatty acid. The word trans means across in Latin. Trans fatty acids produced by this process can combine with other fatty acids to make an industrially produced trans fat. You might be surprised to know that industrial hydrogenation process generates a family of trans fatty acids that are completely different from what tends to be produced naturally by plants and animals. So, industrially produced trans fatty acids is a synthetic molecule that has hydrogen atoms on either side of the double bond, resulting in a straight carbon chain. And industrially produced trans fatty acids is a molecule produced by partial hydrogenization that contains at least one trans fatty acid chain. So comparing molecules. So most fatty acids produced naturally by plants and animals, the hydrogen atoms are always on the same side of the double bond, resulting in bent molecules. The double bonds occur after carbons 3, 6, or 9 when counting from the omega end. This accounts for the omega-3, omega-6, and omega-9 fatty acids. The number of carbon atoms in the fatty acid chain are always an even number. But industrially produced trans fatty acids, these hydrogen atoms are on opposite sides of the double bond, resulting in straight molecules. The double bond can occur after almost any carbon in the chain, but especially after carbons 8, 9, 10, 11, 12, and 13. The number of carbon atoms in the fatty acid chain could be an odd or even number. So biochemists and nutritionists are concerned because the molecules of trans fatty acids are so different from natural fatty acids that our bodies need to stay healthy. Nobody knows all the effects of these substances have on the human body. One known property is linked to the fact that trans fatty acids have straight carbon chain of carbon atoms. This means that these molecules have some properties in common with saturated fatty acids found in butter, grease, beef, and coconut oil. Because the molecules tend to be solid at room temperature, they have a greater likelihood of clogging your arteries. Eating foods rich in saturated fats or trans fats should be avoided for the same reason that bacon fat should be poured down the drain. It will clog up the pipes. Deposits that develop inside the arteries that lead to heart and brain can cause heart attacks and strokes. After the component of the food are also contribute to the buildup of fat deposits in blood vessels is dietary cholesterol. Studies from all over the world indicating that industrially produced trans fatty acids are an even greater risk for heart disease than saturated fats. A study in Denmark indicates that gram for gram, industrially produced trans fatty acids contribute to more than 10 times greater risk of developing heart disease than do naturally produced saturated fats. So dietary cholesterol is a substance found in food from animal sources. So finally, making healthy food choices. Fats and oils are a major source of energy in our body. These substances play a key role in the operation of our nervous system and in other essential body functions. However, it is important to choose foods that have moderate amounts of unsaturated fats and acids, such as monosaturated fatty acids found in olive oil, or the omega-3 fatty acids found in fish oils and flaxseed oil. Saturated fats, industrially produced trans fats, and dietary cholesterol are all substances that can significantly increase your risk of heart disease. It is best to choose the foods that you have with the lowest amounts of these substances. Thanks so much for watching, and we will see you in class.